Alright, we have a truss here that we've been asked to find three forces, three different member forces. And let's see here, we've got BC, that's right here, AH, that's the vertical at the far left, and HG. We're told some information here about the link support at G has a tensile force of 59 kips, and the vertical reaction at A is 28 kips acting downwards. Well, now wait a minute, what about, that's a pin support, what about the horizontal component? Let's just check something out here real quick. And let's look at the global free body diagram. That means we're going to cut away all of the supports, but we'll not cut into the structure itself. And so we'll just simply represent the whole truss as a box, and we'll put on our applied forces. That's the left to right, 11, 12, and 8 kips applied load. And then let's see, AY is a vertical, AX is horizontal, and G is that short link. It's a little two force member, right? Pin, pin, it's in tension, it's vertical. Tension means pulling away from the body, so it would have to be going up at 59. Well, let's check that out briefly. If you were to sum moments about A, that's over here at the far left, the 11, the 12, and the 8 all want to spin in a counter, no, not counter, they want to go in a clockwise fashion about A, and that means that this reaction at G has to be pulling up. Oh, it's pulling up, which means that the link is pulling up on the structure. That means the structure is pulling down on the link, putting it into tension. Right? So that part all makes sense. 59 is a lot more than 11 plus 12 plus 8. That would be 31. So that's one reason to know that at A, the vertical is acting 28 kips, acting downwards. But also, if we were to sum moments about, well, let's not sum moments about G. Let's sum moments about B. The 59 goes through there, the 11 goes through there, the 12 and the 8. Oh, well, that doesn't tell us anything about AX. Let's go back to summing moments about G. Wait a minute, that doesn't help any. Oh, but we've got sum forces in the X, and there are no X forces anywhere else, so AX has to be 0. That's why they didn't tell us anything about that in the problem statement. That was supposed to be obvious to us, or maybe not obvious, but easily determined. So there's your global free body diagram. Now, whether we need the reactions or not is kind of an interesting question. We never really know until we try to go execute things, right? It's a truss. We could do all kinds of different free body diagrams. We'll have to do something. We could do the so-called method of joints, but man, if we do that and we're here in the middle, we might have a long process to get there. If we could do this with one section, that would be pretty cool, but if I cut through, I can't cut through all of them at once. I'm going to have to do this maybe in multiple occasions, or multiple free body diagrams. So let's cut through this panel, GFBC, and get then, and let's take the right hand section here. So let's cut through the GFCB panel and take the right hand free body diagram that results, and let's see what happens when we do that. We'll do this little part here, this little part here, and I kind of like showing all the truss members, and there's not that many to have to show. Alright, so there's that portion. That's kind of, if we went up to the global free body diagram, we'd be cutting right there too, right? Cut that, and we take away what was on the left, and we have to put its effect back into the system. Okay, well, when we do that, note, if we were to sum moments about point C, the 8 wants to go in a clockwise fashion. That means that our top chord, FG, is going to have to be pulling, oh, it's in tension. How about that? And if I sum forces in the vertical, the diagonal is the only one that has any vertical component, and these two forces, 12 and 8, are both going downwards. That means the vertical component of CG has to be going upwards, so it's also in tension. And note that when those two, we follow their lines of action, they intersect at G, and if I were to spin this thing about point G, the 12 and the 8 are want to go in a clockwise fashion, so that means BC has to be going in the other way, and we know immediately how we're going to go find BC. That we're going to some moments about G, because that gets rid of both FG and CG, which we've not been asked to find, and so we're going to have BC times its moment arm. That height is 12 feet, so that's 12 feet times BC. That's a plus, and then we'll have minus 12 kips times its moment arm of 15 feet, minus 8 kips times its moment arm of 30, 15 plus 15. Set that all equal to 0, and therefore we'll find out that BC in the equation will be a positive, I think it's 35, but let's double check. 35 kips, 8 times 30 plus 12 times 15, divide by 12, and we get 35 kips. Again, positive indicates as shown, which means that it's in compression. All right, so there's that one. Then we come and we look at these two. Well, hey, they're connected to the same joint. Why not go cut away the rest of what was there at H, and look what's going to happen here. We'll have only then HG. I don't know if it's in tension. I'm just going to show it that way. And AH, I'll say that that's in tension. And wow, if I sum forces in the Y, take upwards positive, I have minus AH. I got nothing else. Set it equal to 0, so therefore AH must be a zero force member. Likewise, when we sum forces in the X, we're going to get HG and nothing else, and so that has to be then therefore also a zero force member. That's how you derive that rule of thumb. Only two members framing into the joint, well then they're both going to be 0 because I don't got any other forces. Now if I were to put a force somehow at this joint at some oblique angle, then HG and AH would not be 0, but right now they are. There are no applied forces at that joint. There's only two members that are in there, that come in there. They both have to end up being zero force members, and so there's your 3 member forces that are asked for in this particular item.